Let's now continue our development of a reliable data transfer protocol. In the first part of this two-part development, we considered a channel that can corrupt messages. Now we want to consider a channel that can both corrupt and lose messages. Because datagrams can be discarded in router buffers in the face of congestion, this need to communicate when packets can actually be lost between senders and receivers, that's a very important real-world consideration we're going to want to be able to address. Now, the good news is we have just about all the mechanisms that we're going to need to do so. Let's get started. We now want to extend our reliable data transfer protocol to cover the case that not only can the channel corrupt messages, but the channel can also lose messages. And this is going to apply both to the data flowing from sender to receiver, as well as acknowledgments that are flowing from the receiver back to the sender. And before developing our RDT 3.0 protocol, which will handle the case of lost packets, let's ask ourselves, what do humans do in this case? What do you do when you say something to someone who's supposedly listening to you and you get no response back? Well, if you're like me, you say something, the listener doesn't react, a little timer maybe goes off in your head, and you just repeat what you said. That notion of setting a timer, having a timer time out, and then retransmitting, re-saying what it is you said, that's going to be at the heart of our RDT 3.0 protocol. Most of the work's going to be done at the sender, and so the sender, after transmitting, is going to wait some reasonable amount of time for an acknowledgement to be received from the receiver. If no acknowledgement is received within this amount of time, the sender is simply going to retransmit. The one change we're going to have to make is that the receiver is going to need to indicate the sequence number of the packet that's being acknowledged. And this is a difference from RDT 2.1 and 2.2, and you might want to think about why that's the case here. Now, it could be the case that the packet or the acknowledgement were not lost, but actually just delayed. In this case, the retransmission that the sender just made is going to be a duplicate. But the good news is that we've already introduced the notion of sequence numbers to handle the case of retransmissions. And lastly, we're going to need to introduce the notion of a countdown timer, which will generate an interrupt after this reasonable amount of time so that the sender can perform the retransmit action. Here's the finite state machine for the RDT 3.0 sender. It has the same four states as our RDT 2.1 and 2.2 senders, and the cycling among states for the case of no errors is the same as well, except that the sender starts a timer when it sends a data packet and stops the timer when it receives a data packet. These timer operations are highlighted in yellow here. Well, let's consider next what happens when the sender's waiting for an acknowledgement for packet number 0, and now a timeout occurs. Well, let's remember what's happened. The sender sent a packet with sequence number 0. It's waited this reasonable amount of time. A timeout's occurred, and so all the sender needs to do in this case is resend the packet and start a timer again. And in the case that a corrupt packet arrives, the sender will just ignore this, essentially treating the corrupted packet like a lost packet that will be recovered by a later timeout retransmit. And in the case of an ACK1 packet arrival, well, that's an ACK1 for a packet that's been previously acknowledged, so we can just ignore that as well. Now, if an ACK has been received, and so the sender has transitioned to the wait for call 1 from above state, and a packet arrives from the receiver, that packet can just be ignored because we know we've got an ACK0, and so now the sender's waiting for another piece of data to come down from above, which will be labeled 1. Once that data arrives from above, again, a packet is sent, the timer's started, and the sender transitions to the wait for ACK1 state. And in the case of either a timeout or a packet that's corrupt or a packet that is ACKing 0, we have a mirror set of operations for what the sender did when it was in the wait for ACK0 state. Now let's take a look at our RDT 3.0 in action. And the way we're going to do this is by showing the sequence of message exchanges between the sender and the receiver. Sender on the left, receiver on the right, and the time axis going down. So everything gets started with the sender sending a packet labeled 0, propagates over to the receiver receives packet 0, sends acknowledgement 0, that propagates back to the sender. The sender then receives ACK0, sends packet 1, and so on. Let's next look what happens in the case of packet loss. So let's start again with packet 0 being sent from the sender to receiver. The receiver sends an acknowledgement 0 back, which is received at the sender. The sender then sends packet with sequence number 1, which is lost. Now at this point, the sender's done the sending, the receiver's waiting for a packet. Nothing's going to happen until a timeout occurs at the sender. We see that here. When the timeout occurs, the sender resends packet 1, which propagates to the receiver, and so on. Well, that covered the case that a message going from sender to receiver is lost. Remember, the channel can lose messages in either direction. Let's take a look at what happens when ACKs are lost. So in this example, everything occurs without errors until an ACK is lost. Now, at this point, there are no messages in the channel. The sender, well, the sender's sent the packet, doesn't know what happened to it. The receiver has sent ACK1, is waiting for the next packet. The loss has occurred, so nothing's happening at this point except the timer's ticking. Eventually, that timer's going to time out. When the timer times out, the sender's going to resend packet 1. Packet 1 propagates over to the receiver. Now at the receiver side, the receiver says, hey, I just received packet 0 earlier, so I detect a duplicate. It would not deliver the packet 1 data up to the application layer. Instead, it simply sends an ACK1 back, and so on. Recall that we'd said earlier that the sender is going to set a timeout interval to some reasonable amount of time. How long should that be? Well, we'll come back to this when we look at the question of TCP, but there's going to be a possibility of what we might call a premature timeout because either the message or the ACK has been delayed in getting back to the receiver. Let's now see how the sender and receiver handle this case of a premature timeout. In this example, everything's proceeding without error initially. We see ACK1 propagating back when the timer times out, prematurely in this case, since ACK1 is just about to arrive. On timeout, the sender will resend packet 1, which is received at the receiver, detected as a duplicate and so not delivered up to the application layer, and the receiver responds with an ACK1 to the sender, re-acknowledging packet 1. Now, let's go back in time and see what happens when the sender receives the original ACK1 message. Well, this is what it was waiting for, and so it then sends the next packet, 0, which will be received and acknowledged at the receiver. Last, let's take a look at what happens at the sender when it's waiting for an ACK0 but receives a duplicate ACK1. In this case, according to our finite state machine, the sender simply ignores this duplicate ACK1. Well, we should pat ourselves on the back. We've actually got a reliable data transfer protocol that will work over a channel that can lose and corrupt messages. And it's almost even workable in practice. To see what we still need to do though, let's take a look at the performance of RDT 3.0. The performance metric that we'll be interested in is utilization, the fraction of time that the sender is actually busy sending bits into the channel. Let's see now how we can compute that, and let's start with an example. Imagine we've got a 1 gigabit per second link. The propagation delay is 15 milliseconds, and let's imagine that each packet is 8,000 bits long. If you recall from chapter 1, the time it takes to transmit bits into the channel is simply the length of the message divided by the transmission rate, meaning that it takes 8 microseconds to transmit a message into the channel. Let's take a graphical look at the operation of RDT 3.0. At t equals 0, the sender transmits the first bit of a packet into a channel. That bit is then going to propagate over to the receiver. Finally, when the last bit is transmitted at the sender, arrives at the receiver sends the acknowledgement packet, and the acknowledgement packet, which we'll just assume is a single bit, propagates back to the sender. At time t equals RTT plus L over R, the ACK arrives, and at this point, the RDT 3.0 sender can send the next packet. Well, with this visualization in mind, we can pretty easily compute the utilization of the sender. The amount of time from when the sender first starts transmitting a bit until it receives the acknowledgement is L over R plus RTT. The total amount of time it's actually sending bits into the channel is L over R, and therefore the utilization is L over R over RTT plus L over R. Now, if we plug in the numbers, we see that the sender utilization is 0.00027, which is really bad performance. What we're seeing here is that the protocol limits the performance of the underlying infrastructure. Remember, we've got a gigabit per second channel, but we're hardly utilizing it at all because of the stop and wait behavior of RDT 3.0. This is what we're going to want to fix. And the fix is going to be to introduce a technique which is known as pipelining, which will allow the sender to have multiple in-flight and yet to be acknowledged packets propagating between sender and receiver. We see that pictorially here. In order to do this, we're going to have to increase the range of sequence numbers and also introduce more buffering at both the sender and the receiver. Coming back to our earlier example, we see here that if we allow a pipelining of 3 packets in the pipeline, we're able to increase the utilization of the sender actually by a factor of 3. We'll look at 2 approaches for pipeline reliable data transfer: go back in and selective repeat. We'll see that they use the same mechanisms that we've seen already: sequence numbers, acknowledgements, checksums, timeout, and retransmit, but they'll use these mechanisms slightly differently. Let's start by looking at go back in. Our pipelined go back in sender is allowed to have a window of up to n transmitted packets that have not yet been acknowledged. And we'll need to include now a k-bit sequence number field in the packet header. The sender's view of the sequence number space is shown here in this diagram. The green sequence numbers correspond to packets that have already been acknowledged. We see a window of size n. The yellow packets have been sent but not yet acknowledged, and the blue sequence numbers, those are sequence numbers that are available for use but haven't yet been used by the sender. And the white sequence numbers are not usable. They fall outside of the window of size n. Go back in operates with what are known as cumulative acknowledgements. When the sender receives an ACK with a sequence number of n, it acknowledges all packets up to and including sequence number n. And as we'll see, TCP actually uses this kind of cumulative ACK. On receiving an ACK of n, the sender is going to move its window forward, and now the left side of the window is going to begin at n+1. Because packets can be lost, the sender will need just a single timer for the oldest in-flight packet. When a timeout occurs, the sender is going to retransmit packet n and all packets with higher sequence numbers that have currently been sent. The go back in receiver, it's pretty simple. Whenever it receives a packet, it's going to send an acknowledgement back for the correctly received packet so far that has the highest in-order sequence number. If it receives an out-of-order packet, it could discard that packet or buffer it, but in either case, it's going to re-acknowledge the packet that has the highest in-order sequence number so far. The receiver's view of the sequence number space is pretty simple. All it needs to do is track the sequence number of the next in-order packet expected to be received, and that's shown by RCV base here. Okay, so now let's watch the go back sender and receiver in action. We're going to skip the finite state machine specification for go back in. You can check out the book or the PowerPoint to pick that up. So we're going to assume a window size of 4, and at t = 0, the sender sends packets 0, 1, 2, and 3. And shown in this scenario here, packet 2 is going to be lost. At the receiving side, packet 0 is received, ACK 0 is generated, packet 1 is received, ACK 1 is generated, and packet 2 is lost. And so when packet 3 is received, an ACK 1 is sent. That's the cumulative acknowledgement that we learned about. So ACK 0, ACK 1, and the duplicate ACK 1 now propagate back from the receiver to the sender. When ACK 0 is received, that's the lowest number sequence in the window, so now the window can move forward on the sending side. When ACK 1 is received, the window moves forward again and packet 5 is sent, and so on. And lastly, let's take a look at what happens when ACK 1 is received here. In this case, this is a duplicate ACK and it's going to be just ignored at the sender. Now let's take a look at the receiver and see what happens when packets 4 and 5 are received. In both cases, these will be discarded because packet 2 has yet to be received, and the receiver will respond with a duplicate ACK 1 acknowledging the last correctly received in-order packet, which was packet 1. Now recall that packet 2 had been lost earlier, so eventually there'll be a timeout for packet 2, and packets 2, 3, 4, and 5. Those within the current window are going to be sent. They'll propagate over to the receiver and acknowledgments will be generated. Well, an important mechanism in Go Back N was the use of cumulative acknowledgments, and as we noted, cumulative ACKs are actually used in TCP. An alternate ACKing mechanism would be for a receiver to individually acknowledge specific packets as they're received. This mechanism is at the heart of the selective repeat protocol. So in selective repeat, a receiver individually acknowledges all correctly received packets and can buffer packets as needed for later delivery in order to the upper layer. At the sending side, we can think of the sender maintaining a timer for each individual unacknowledged packet, and when the sender times out, it's going to retransmit that individual packet. Let's now take a look at how the sender and the receiver look at their sequence number spaces. On the sending side, again, we see a window of size n, and within that window, there will be sequence numbers corresponding to packets that have already been acknowledged, packets that have been sent but not yet acknowledged, and then there'll be sequence numbers shown in blue here that are usable, but the sender has not yet received data from the application layer to send yet. On the receiving side, again, we have a window of size n. To the left of that window, we have sequence numbers corresponding to packets that have already been received and acknowledged. The receiver window will begin with the sequence number of a packet that's expected but not yet received, and there may be packets that are received, shown in red here, that have already been acknowledged, but they haven't been delivered because there's earlier data that has not yet been received. Well, you've probably already got a good idea how the selective repeat sender and receiver work, but here are the specifications. On the sending side, when data is available from above, if the next available sequence number is available and not used and within the window, the packet is sent. On a timeout event, the sender resends packet n and will restart the timer, and if an acknowledgement is received for a message in the window, the sender is going to mark that packet n as being received, and if it's the smallest unacknowledged packet in the window, it's going to advance the window base forward. On the receiving side, if a packet's received and it's within the window, an individual acknowledgement, a selective acknowledgement, is sent. If it's out of order, it will be buffered for later delivery. And finally, if the packet's in order, its data will be delivered, as will any buffered data that can now be delivered in order. If the packet falls to the left of the window, the receiver's already acknowledged this, but will send another acknowledgement in case that earlier acknowledgement had been lost. Otherwise, any received packet will simply be ignored. And now let's take a look at the selective repeat protocol in action. And again, for this example, let's assume the window size is 4. So at t equals 0, the sender sends packets 0, 1, 2, and 3. They propagate over to the receiver. Packet 2 is lost, as in our earlier example. Now each of packet 0, 1, and 3 will elicit its own individual acknowledgement. And the difference between selective repeat and go back n should be clear here. When packet 3 is received in this case, it's buffered and an acknowledgement is sent specifically for packet 3. So the acknowledgements for packets 0, 1, and 3 propagate back to the sender. On the receipt of ACK 0, the sender will then advance its window forward 1 and send packet 4, which will propagate over to the receiver. Similarly, when ACK 1 is received, the window will be advanced and packet 5 will be sent. When the acknowledgement for ACK 3 arrives, the sender will record that ACK 3 has arrived, but the window will not be moved forward because packet 2 has not yet been acknowledged. Well, packet 2 was lost earlier, so eventually there'll be a timeout event for packet 2, and in this case, the selective repeat sender will just retransmit packet 2. That will propagate over to the receiver. In this case, it's not lost. The receiver receives packet 2, delivers packet 2, and also delivers the content from packets 3, 4, and 5, and sends an acknowledgement for packet 2. So there we have it. We've finally developed a reliable data transfer protocol for a sender and a receiver that want to communicate over a channel that can lose or corrupt messages flowing in either direction. We saw the use of a common set of techniques: acknowledgements, checksums, sequence numbers, timeout and retransmit mechanisms. And we've studied this primarily in the context of the transport layer, but again, remember this need to reliably communicate happens at the application layer, happens at the network layer, and it happens at the link layer. And so this is why this is really a top 5 networking problem that we've now solved. So coming up next, let's take a look at the reliability mechanisms in the TCP protocol.